This film is an actual record of modern astronomy and of men building and using the great 200-inch telescope at Palomar Mountain, probably the most precise and significant engineering achievement of all time. For our world's origin and destiny is linked with the atomic mysteries of distant stars. The ensuing picture is a tribute to Dr. George Ellery Hale and those other quiet and patient men who are bringing more light to this Earth. This refracting telescope is the type with which most people are familiar. It is similar in principle to the first instrument built by Galileo in 1609, having a convex lens or objective in the far end of a long tube. However, this lens with a diameter of 6 inches is a giant compared to the small spectacle lens which Galileo used in the first telescope. A convex lens gathers light, bending and converging it to a sharp focus where an image is obtained of a distant object. A second lens, or eyepiece, magnifies the image for visual observation. Through telescopes of this type, an observer can study familiar objects like the moon. And by changing to an eyepiece of greater magnification, he can study a single lunar crater in detail. There are other moons too, such as these 4, which Galileo was the first to observe, revolving around the planet Jupiter. Saturn, with its rings and bands, is one of the most striking planets. A telescope also reveals thousands of stars which the eye alone could never see. Dr. Seth Nicholson now demonstrates how telescopes are supported on an axis parallel to the Earth's axis. North and south bearings provide support for the axis about which the telescope rotates. As the Earth rotates, the telescope is moved automatically in the opposite direction. All through the night, the telescope tube stands relatively fixed in space, pointed toward the stars, while the Earth spins beneath it. This steady motion is provided by a driving mechanism which turns the telescope tube just as an ordinary clock turns its hands. Larger telescopes require larger and more accurate driving clocks. This mechanism, completed in 1908, drives the 60-inch telescope of the Carnegie Institution's Mount Wilson Observatory. Great telescopes like the 100-inch reflector are housed in huge domed structures which can be opened and turned toward any portion of the sky. The 100-inch telescope is of the reflector type, first developed by Newton in 1671. The astronomer actually looks into the side of this instrument. Instead of an objective lens, a concave mirror 100 inches in diameter is placed in the bottom of the telescope tube. Another mirror, a smaller flat one, is placed at a 45-degree angle in the upper end of the tube. Light from the stars shines down the telescope tube and is reflected from the concave mirror in a converging beam back up to the flat mirror, which then reflects the concentrated light to a focus at the observing position near the side of the tube. These reflectors concentrate and focus light just as the convex lens does in the Galilean-type telescope. Dr. Edwin Hubble, on a movable platform, lines up the massive telescope as he begins a cold night's work. Having turned the telescope with electric motors to the desired position and coupled the driving clock, he focuses the image and centers the object to be photographed. He attaches a 5 by 7 inch plate holder, just as one would on an ordinary camera. For large telescopes with their great magnification and light-gathering power are used almost entirely as cameras to photograph the wonders of the heavens. When all adjustments have been made, Dr. Hubble signals his assistant to turn out the lights inside the dome, which would fog the sensitive photographic plate. As the lights go out, he pulls the slide, and the huge instrument makes a time exposure of the selected object. This unusual star cluster in the constellation of Hercules is visible through a large telescope. These visible stars can be photographed in 5 minutes. With an exposure of 37 minutes, hundreds of stars are recorded which the eye could never see directly through the instrument. If the exposure time is increased to a few hours, more than 50,000 stars are revealed. The faintest of these stars is no brighter than a candle would appear at a distance of 8,000 miles. This is an enlarged photograph of the planet Mars taken with a 100-inch telescope, and no trace of the so-called canals is revealed. However, this drawing shows long intersecting straight lines which have been seen by only a few observers. After Mars had turned relative to the Earth, this drawing was made. If a more powerful telescope could just photograph these elusive lines, the controversy as to whether they actually exist would at least be settled. Interlaced among distant stars, a photograph with a 100-inch telescope shows wispy clouds of nebulous material. The Crab Nebula is the result of a stellar explosion about 1,000 years ago. Photographing it through different colored filters reveals a different structure in each case, giving a clue to its chemical and physical composition. Other structures which looked like nebulae were observed years ago with smaller telescopes, but their real nature was unknown. Slightly larger telescopes revealed cloudy masses apparently whirling around a central body, and these were named spiral nebulae. Moderate magnification gave this magnificent picture of the great spiral nebula in Andromeda. If we examine one part of the photograph and enlarge it, this blurred detail is obtained. However, when this same area is photographed with a telescope having a larger mirror like the 100-inch, a sharper picture is obtained, and our nebulous cloud becomes myriads of individual stars. The study of thousands of these so-called spiral nebulae has proved that they are actually vast island universes, billions of miles in diameter, and similar to our own galaxy. Each of these distant blurred dots is a spiral nebula made up of millions of stars like our own universe, but they are so far away that their light must travel over 100 million years before reaching the Earth. The light from any one of these nebulae can be analyzed by photographing its spectrum through special attachments on the telescope. Here, Mr. Milton Humason, another Mount Wilson astronomer, prepares to study one of his spectra under a microscope. This tiny photographic plate was exposed with a 100-inch telescope for a total of 22 hours on 3 successive nights. By examining and measuring such a plate through a microscope, the astronomer can accurately determine the chemical composition, temperature, relative velocity, and distance of remote nebulae. This is done by comparing the exposure of the nebula in the center with reference bands of known elements on this Earth, which have been double exposed on the plate, top and bottom. The astronomer learns about the origin and transmutation of elements and the expanding universe, all from tiny negatives like this one. The sun is so much brighter, its spectrum can be photographed directly through a prism showing all its brilliant colors. Dr. George Ellery Hale, outstanding astronomer and authority on the sun, was former director of the Yerkes and later the Mount Wilson Observatory. He pointed out that a great industrial country like the United States, which built great skyscrapers, dams, ships, and bridges, should use her resources to build even bigger telescopes than these on Mount Wilson. In 1928, Dr. Hale's vision and enthusiasm inspired the Rockefeller Foundation to grant $6 million to the California Institute of Technology for the construction of a 200-inch telescope. The Institute, with its fine laboratories and eminent leadership, had already made outstanding contributions in the fields of engineering and science. Dr. R.A. Millikan headed the Institute and recognized the unity of science that brought electrons and universes together. The Caltech campus is located below Mount Wilson and about 100 airline miles from the site of the 200-inch telescope. An astrophysics building was constructed to provide offices and laboratories for the staff of the 200-inch project and general instruction and research in astronomy, the stars now being a recognized field for the study of chemical and physical sciences. Russell W. Porter, engineer, astronomer, and explorer, was brought from retirement to help design the 200-inch telescope. Plans had been suggested earlier by Francis Pease, who designed the 100-inch telescope. Marc Serrurier evolved the remarkable structural design of the skeleton tube, and many invaluable contributions were made by engineers, scientists, astronomers, and even amateur telescope makers from all over the world. The 200-inch telescope grew from ideas in men's minds and gradually took shape on paper under Porter's skillful hand. One of the many unusual features was a horseshoe bearing on the upper end of the axis. A 1/100th scale model was built to demonstrate and evaluate the design. It shows the north and south bearings on which the telescope can rotate east or west parallel to the Earth's axis. A second movement permits the instrument to swing south or north. The 200-inch mirror is at the bottom of the skeleton tube. On top of the astrophysics building, a larger working model, 1/10 size, was built from the 200-inch blueprints. Bruce Rule, project engineer for the 200-inch telescope, checks the controls of the working model and demonstrates how the dome with its shutters can be rotated electrically to any desired position. The telescope also responds to electric controls. Starting from its cradle in the horseshoe, it moves from north to south. A second movement from west to east enables the telescope to be pointed to any part of the heavens. Of course, this small model does not enable the observer to ride inside the tube at the top of the telescope, which will be possible for the first time with a 200-inch. The brilliant 20-inch concave mirror in the bottom of the tube makes this model suitable for general observation and instruction purposes. Following the construction of the 1/10 scale model, work commenced on the numerous gears, supports, and controls for the big telescope itself in the machine shop located on the Caltech campus. The most precise work which was done here set new records in instrument making. The glass disc for the mirror, after repeated tests and failures, was finally cast of Pyrex glass in a special furnace of the Corning Glass Works in New York State. The Pyrex glass offered rigidity, minimized expansion due to temperature changes, and permitted accurate grinding and polishing of its surface. An optical shop for figuring the large disc into a perfect mirror was built adjacent to the machine shop on the campus. Dr. Max Mason, on the right, chairman of the 200-inch Observatory Council, worked closely with Dr. John A. Anderson, who had the responsibility of fashioning the crude disc into a perfect reflecting surface. Long ago, Dr. Anderson ground his first lens just as Galileo had done, and as many amateur telescope makers still do, rubbing one disc of glass across another day after day, using emery and water as a cutting agent. Dr. Anderson also knew the problems of grinding glass by machine and how to design those machines and supervise their use so that they would grind glass faster and better than by hand. A machine like this would grind and polish a 3-inch lens in several hours. As larger pieces of glass were handled, such as this 24-inch auxiliary mirror for the 200-inch telescope, only specially built machines could do the job. The actual grinding tool consists of small tile blocks cemented to sponge rubber, which in turn is cemented to a steel base plate. This permits more uniformly distributed pressure on the glass being ground. A series of cutting and polishing tools is used in conjunction with progressively finer abrasives. The coarse abrasive digs out the glass to approximately the right curvature. Then the finer abrasives are used to remove the scratches left by the coarser. And finally, the scratches that are too fine to be seen by the eye are removed by the red rouge of iron oxide. Here are some of the tools used to grind and polish the 200-inch mirror, varying from 1 to 17 feet in diameter and faced with different types of blocks. They are inspected by Marcus Brown, who was chosen to supervise the actual work. While all grinding and polishing operations were done behind locked doors, visitors were permitted to view the progress of the work from a glassed-in balcony at one end of the large room. From this vantage point, visitors could watch the massive machine that ground and here is polishing the 200-inch disc. This work had been going on precisely and patiently over a period of 11½ years. Dr. Lee DuBridge, the new president of the California Institute of Technology, watches the polishing with keen interest from the visitor's balcony. Dr. Ira Bowen is a most critical observer, for he is the director of the combined Mount Wilson Palomar observatories. The nearly finished Pyrex disc, 200 inches in diameter and 24 inches thick, weighs 14¾ tons. The waffle-like pattern is the rib structure of the back, which can be seen here through the transparent glass. Later, a brilliant reflecting surface of aluminum will be added, making a perfect mirror. The red rouge and water mark the final stage of polishing. The utmost diligence is necessary to prevent any gritty substance from contaminating the mixture, which might scratch the mirror's surface enough to set the entire project back several years. A carriage which holds the polishing tool moves over the disc. Adjustments are made for the proper motion of the tool. A master switch is thrown which starts the disc rotating. Over 30 tons of various abrasives and polishing compounds and 180,000 man-hours of devoted labor had been required to remove the 5¼ tons of glass which brought about this present parabolic curvature. The curvature of the mirror was calculated for a focal length of 55 feet, which, combined with a diameter of 200 inches, gives a speed rating of f3.3. The periods of polishing grew shorter and shorter, and the testing more frequent as greater accuracy was achieved. From several days, each polishing period had been cut down to several hours, after which tests were made to determine further corrections. Testing requires that the mirror be cleaned of all rouge and thoroughly washed. Surplus water is then wiped off, and it was also standard practice to wash and scrub the machine after each operation. Even the floor was scrubbed daily, if not more frequently. The mirror is tilted up while still on the carriage of the grinding and polishing machine. In a vertical position, it will face a test platform 110 feet away, seen on the right. The method of testing the mirror to 2/millionths of an inch seems almost impossible, but it is done very simply with a tiny beam of light. A small light bulb is enclosed in the housing on the right and shines out through a pinhole towards the mirror. The curved mirror, even though the coating hasn't been applied to increase its efficiency, reflects some of the light from the pinhole directly back to the observer. A movable knife edge in front of him intercepts the returning rays. This permits the observer to analyze the light from different portions of the disk. As Brown adjusts the knife edge, this pattern of light and shadow which he sees reveals the true condition of the curvature of the mirror. These are actual shots of the optical tests on the 200-inch disc. To measure the mirror surface accurately, a special screen is placed in front of it, which has numbered openings at known distances from the center. Now, accurate readings can be made and recorded. Later analysis of this data will indicate the adjustments to be made on the polishing machine to make a perfect telescope mirror out of the great glass disc. After the polishing of the front surface of the mirror was finally approved, Marcus Brown looked with satisfaction on the back of the mirror, which he hadn't seen for more than 10 years. The ultimate curvature of the mirror now depended upon 36 separate supports evenly spaced over its back. Each of these 36 supports will have its 1,000 parts so carefully made and adjusted that regardless of how the mirror may be rotated or tilted in the huge telescope tube, each support will carry its share of the weight and thus minimize distortion of the heavy mirror due to sagging. Even after the mirror is installed on Palomar Mountain, many months will be required to make the final additions and adjustments to the most sensitive cradle ever built by man. As the mirror is swung around to place it in its steel cell, the structure, thickness, and concave surface are clearly seen. The hole in the center can be used in conjunction with a positive auxiliary mirror in the upper center of the tube. This will reflect light back through the hole for a longer effective focus and consequently greater magnification. The mirror is now placed in the cell, which in turn will be bolted to the bottom of the 55-foot telescope tube at Palomar. The ingenious design of the grinding mechanism facilitates the movement of the mirror. Dr. Anderson undoubtedly feels a justifiable pride as the finest optical accomplishment in his or any man's career has been completed. With a giant mirror firmly anchored to the steel cell, it is finally ready for the 160-mile trip to Palomar Mountain, where the dome, telescope mounting, and controls had already been completed. The lifting crane was carefully rigged to lift the ponderous weight without strain or jar. "35 tons of the greatest achievement in telescope making hangs by 12 slender cables, and its difficult movement to Palomar will be the last of the many risks in its development." The disc is lowered onto a specially constructed trailer which will ease the load along the highways, bridges, and a specially built road up to Palomar Mountain itself. For added protection, after the lifting rig is removed and the load secured to the trailer, a huge box of 2-inch thick planks is placed over the most valuable piece of glass in the world. The journey was scheduled to start at a secret hour in the night to avoid crowds, traffic congestion, and frequent stops and starts, which would cause excessive vibration and other risks. The sunny morning of November 18th, 1947, found the special convoy rolling smoothly down the coast route from Los Angeles towards San Diego. Oncoming traffic had been stopped or rerouted miles ahead by the efficient California Highway Patrol, as the width of the trailer required 3 lanes of the highway. Many problems had been foreseen and special equipment constructed months ahead. This truck, also used to help push the trailer up steep grades, is now pulling in one of 2 dollies which are to be bolted to the sides of the trailer so that the heavy load can be distributed more towards the stronger side of a bridge that lies just ahead. Each of these dollies has 8 heavy-duty tires and now enables the load to be distributed over a total of 58 wheels. This bridge seems flimsy as the ponderous caravan approaches it. Engineers, scientists, truck drivers, and news photographers collectively hold their breaths as the powerful tractor slowly tows its precious cargo. The deflection of the bridge was measured and found to be 3/8 of an inch. Even the seagulls at San Juan Capistrano stopped to see the great mirror roll along the highway by the Pacific Ocean. A heavy load is pulled and pushed towards the mountain. Palomar Mountain had been selected years previously after many observations as an ideal site for a telescope. The sun shines in Southern California most every day of the year, so we are told, and the 2 days required to move the mirror were only scheduled after the weatherman had promised ideal California sunshine. Actually, rain and sleet beat down upon the covered mirror while going up the steep mountain grade, and at times the driver cannot see more than 50 feet through the heavy mists. In spite of this unusual weather, the caravan is now 4 hours ahead of schedule. By the time the dome itself is reached, a heavy rain is falling. Every man who worked on the 200-inch telescope was outstanding in his field, and the man driving this tractor is no exception. Finally, after years of patient effort, the heart of the telescope is pulled safely into the shelter of the huge protecting dome. Ordinarily, Palomar Mountain is above the clouds, and bright city lights, which have seriously affected the observing on Mount Wilson, do not penetrate this isolated location. The 200-inch telescope was built upon a flat-topped ridge of solid granite. The graceful dome is nearly 12 stories high, measuring 135 feet in height and 137 feet in diameter. A special entrance is provided for visitors, and a glassed-in gallery inside the dome permits them to view the telescope between 9 a.m. and 4 p.m. every day. The light from the stars must first enter the telescope dome through an opening which can be closed by shutters. each of which weighs more than 100,000 pounds. As the shutters slowly open, the outline of Dr. Hale's dream takes shape. The massive outlines of a telescope weighing 1,000,000 pounds, comparable to a bridge or a skyscraper, but built with the precision of a fine watch. Appropriately, when this great instrument was dedicated on June 3rd, 1948, it was named the Hale Telescope. The horseshoe bearing, 46 feet in diameter, the largest bearing ever made, is another miracle of construction, made with other large parts by Westinghouse. The cylindrical cage in the center of the tube permits an observer for the first time to ride a telescope and to photograph the stars directly from the big concave mirror. The massive telescope is controlled by an assistant who stands at a console beneath the instrument. A concrete dummy in place of the mirror permitted checking of all movements, even while the mirror itself was still being polished at the California Institute. An adjustable diaphragm was made to protect the mirror's surface when not in use, and also to act as a variable stop setting as in an ordinary camera. Byron Hill, superintendent of construction, spent 12 years on the mountaintop with his crew, assembling the heaviest precision equipment ever made. Now, at the push of a button, 1,000,000 pounds of telescope respond like a genie to every wish of the operator. Rotation on the axis to carry the telescope east or west depends largely on the horseshoe bearing, which glides on 2 thin films of oil. These oil pads, or flotation bearings, have less than 1% of the friction and deformation of ball or roller bearings. This fast east and west movement is used to bring the telescope to the position desired for starting observations. The power is supplied by a 2-horsepower motor. A second panel controls the movement north and south. The position desired is set by turning a dial to the proper reading, and then the push of a button swings the telescope automatically to the indicated position. This tilting motion in a north or south direction may be continued right into the horseshoe bearing if it is desired to observe objects near the North Pole. Of course, the dome would then be rotated to provide an opening for that position. To minimize the effects of vibration when the dome is turned, the telescope rests on a massive foundation independent of the dome. When photographs are being made, this small 1/12 horsepower motor alone turns the 500 tons of steel and glass to compensate for the Earth's rotation. The motor is connected to the telescope through a maze of mechanical computers, which automatically correct its motion for deformation in different positions and even the effects of atmospheric refraction. The actual position of the telescope is indicated continuously by calibrated dials. The dome can also be turned electrically to any position. 2 of these drive units, each having 2 5-horsepower motors, turn rubber tires which are firmly pressed against the dome. The dome itself rests on 32 4-wheeled suspended trucks, similar to those of a railroad car, but more accurately made. This rapid turning of the dome brings its opening in front of the telescope. Once the telescope is in operation, a robot control moves the dome so that it never intercepts the light about to enter the telescope tube. Looking out through the opening as the dome revolves, a panorama of mountains is seen, including the water supply and power plant for the community on Palomar Mountain. The powerhouse has 3 diesel-electric generators which assure constant current at all times for the telescope as well as the maintenance shops and residences. So the dome and the mounting with their controls were ready for the mirror when it arrived. The mirror and its supporting cell were bolted to the base of the telescope tube on the upper left after the huge disc had received a brilliant reflecting surface of aluminum in the vacuum tank in the background. The back of the mirror cell shows the 36 supports upon which the mirror rests. Each of these supports, with its intricate counterbalanced mechanisms, has been carefully adjusted to carry its share of the load. The telescope tube must be tipped down to see the front surface of the mirror. The cylindrical cage is where the reflected image from the mirror can be viewed and photographed by the astronomer. To enter the cage, the observer must ride up a specially designed elevator. From this vantage point, the diaphragm may be seen as it opens and reveals the mirror with its brilliant aluminum coating, reflecting and concentrating the brightness of a noonday sky. The 200-inch mirror at the bottom of the tube will reflect the light from the stars directly back to the prime focus position in the observing cage, where an eyepiece or a photographic plate may be used. One night in the early part of 1948, Dr. Bowen rides up the elevator and climbs into the observing cage. Controls close at hand and a telephone to the assistant at the console below permit accurate pointing of the instrument. The telescope now turns toward a certain portion of the heavens, and its great reflector looks upwards with the light-gathering power of 1,000,000 human eyes. Dr. Bowen has the thrill of an explorer, methodically preparing for a trip that will lead into the unknown mysteries of space. After numerous careful adjustments, he attaches a sensitive photographic plate so that the film may register what unaided human eyes could never see. The giant Hale Telescope, built from the hard materials of this Earth, becomes lost in the immensity of space, for man's mind, tuned to the frequency of light, is seeking a new meaning and a new destiny, far beyond the stars of the Milky Way. Every new telescope creates more problems than it solves, and even the precise measurements of the astronomer often lead to new mysteries. We know of the atoms that compose the stars, and we know of thousands of universes as large as our own, far out in space. But what caused them, and what exists beyond them? Why do they move at such tremendous speeds? Is there an end to space? The 200-inch Hale Telescope may answer some of these questions.